Hello and welcome to my Calculus CCT. My name is James King and today I am going to be going over question number 7 on page 299 of the school textbook. In this video I hope you, the viewer, will learn about derivatives, ways of finding them, and properties of graphs. The question reads, television consists of 30 complete pictures displayed on the screen every second, giving the illusion of motion. The video signal that creates the picture must include a pulse between pictures to synchronize one picture to the next. This sync signal is modeled using a function of the form a at t equals 20 sine squared t over 1000 pi, where a is the amplitude in volts and t is the time in seconds. The first part of the question is to find the derivative of the sync function with respect to t. The second part of the question asks to find the first value of t greater than 0 for which the derivative is 0, and the third part of the question asks to graph the functions and a tangent to verify your answer from part B. The introduction is useful in giving us the original function a at t equals 20 sine squared t over 1000 pi and the units. T is time in seconds and a is amplitude in volts. The first part can be simplified as find the derivative of the function. The second part is really asking for the first turning point after time starts, and the third part wants a graph to prove our answer. The first part of the question asks for the derivative of the sync function. The derivative of an equation gives the instantaneous rate of change of a function at any point on the x-axis. To find this function's derivative, we can use derivative rules from Unit 2. The first derivative rule is the power rule. This rule states that to find the derivative of a function with an exponent, multiply the coefficient by the exponent and subtract 1 from the exponent afterwards. The bottom two lines show how this will be applied in the problem. Here is an example of the power rule. By starting with x squared, we can multiply the coefficient by 2 since the exponent is 2, and then subtract 1 from the exponent to get the derivative 2x. Notice the tick beside the y on lines 2 and 3. This signals a derivative. Another derivative rule needed is the chain rule. This states that the derivative of an equation with a function inside a function is equal to the derivative of the outside, keeping the inside the same, and multiplying by the inside's derivative. Here is an example of the chain rule. We use the power rule for the outside function, so the coefficient becomes 4 and the exponent becomes 3. We keep the inside as 3x minus 5 and multiply by its derivative, which is 3. The last rule required is derivatives of sinusoidals. This rule states that the derivative of a sine function is a cosine function. I've shown this relationship graphically to give you a better idea of the relationship between sine x and cosine x. Cosine x is the rate of change of the graph sine x. To begin finding the derivative, I can write out the original equation. I can see that there is an exponent, so I'll have to use the power rule. By multiplying 20 by 2, I can decrease the exponent by 1. Also, I need to keep the original sine function the same when doing this. Afterwards, I can use the change rule to differentiate the sine function, and then again to differentiate the fraction inside the brackets. Doing this, I get 40 sine t over 1000 pi by using the power rule. The chain rule then gives me the multiple of cosine t over 1000 pi, and then I do this again for the inside of the brackets and get a multiple of 1 over 1000 pi. A crucial step is simplifying the equation, and a trig identity is the best way to do that. Because my sine and cos functions have the same k value, I can use the identity sine 2x equals 2 sine x cos x. The 2 sine x cos x is what I previously had, by making the sine function's amplitude half its original value and its k value twice its original value, and cutting out the cos function completely. I have something much simpler which is easier for graphing. To finish, simply multiply the lonely 1 over 1000 pi by the amplitude of the sine function. And there you have it. The derivative of a at t equals 20 sine squared t over 1000 pi is a prime at t equals 1 over 50 pi sine t over 500 pi. Now we can do the second part of the question. The question is, what is the first value of t greater than 0 for which the derivative is 0? In other words, this is asking for the first turning point after 0 seconds. To do this, I can simply set the equation which we just derived equal to 0 and solve for t. So if you followed what I just said, your answer should be like this so far. I can get closer to my answer by dividing the left and right sides of the equation by the coefficient 1 over 50 pi. This gives me the same equation, but no coefficient. To get closer to isolating t, I bring sine over to the left side of my equation. It becomes sine inverse or arc sine 0. Sine inverse 0 is equal to 0 and pi and every integer times pi. Since the equation does not want an answer of t equals 0, I use the first positive value of arcsine 0, which is pi. From here we can do some fairly easy math to solve for t. Multiply both sides by 500 pi and you will get the answer t equals 500 pi squared. A sentence answer will give some context. The first value of t greater than 0, for which the derivative equals 0, is 500 pi squared, or about 4,935 seconds. The last part of the question asks for a graph of the functions and a tangent. This is where I will prove that the previous answer is correct. Here I have graphed the original function. At the point on the x-intercept 500 pi squared there is a turning point. Turning points are equal to 0 in terms of instantaneous rates of change, and this is shown by the tangent that is parallel to the x-axis. The second graph shown is the derivative. On this graph, the value of 500 pi squared is 0 on the y-axis. This is not only proof of the answer from part B being correct, but also proof that a derivative is equal to the instantaneous rate of change of the original function. This is a fundamental rule in calculus. Astronomers are individuals who can use calculus concepts with sinusoidal functions. Cepheid variables are stars that pulsate and vary in brightness. They are used for determining the distances to nearby galaxies. By knowing the period which Cepheid stars possess, we can calculate the rate of change of these stars' brightness, which helps us determine properties of the stars at more accurate distances. Thank you for taking the time out of your day to listen to my Calculus CCT, and I hope I taught you something.